Okay, we are live. Welcome everybody to this this important speech prosody series lecture. Today, Gérard will present his lecture, Controlling Probing Generative End-to-End Models, New Opportunities for Research on Prosody. Gérard had his PhD in electronics from the Institut National Polytechnique de Grenoble, and then he became research assistant from the Institut National de Recherche Scientifique à Montréal, Canada. Et il est directeur de recherche d'abord à l'ancien Institut de la communication parlée à Grenoble, et ensuite à Lab depuis 2001, les deux instituts, both laboratories. And it's a great honor on behalf of the Speech Prosody lecture series to welcome Gérard here, because he was my PhD advisor in the 90s. Gérard also worked on human-robot interaction. He has this Nina robot. He describes models and tracks facial movements in his studies. He works also on face-to-face communication, working on patterns of gaze and speech, the prosody modeling, and augmented speech communication. Thank you so much for being here, Gérard. The floor is with you.
Okay, so thank you, Plinio. So as Plinio has said, I'm senior researcher at Lab in Grenoble, France. And in the framework of the webinars organized by the ISCA Special Interest Group on Speech Prosody, I will elaborate on opportunities offered by end-to-end generative models for helping us understanding forms and functions of prosody. So you will listen a bit of a synthesis of French language, but I hope that you will still understand, at least appreciate the prosody. This was synthesis. So before moving into the scientific presentation, just a few words. Deep learning has invaded all fields of science, from computer vision and signal processing, natural language processing, neuroscience, physics, to more sensitive decision-making, such areas as economics, health, education, and so on. Some authors even predict the death of human expertise because of the ability of this system to process raw data with minimum or even no human supervision. Should scientists be all machine learning experts? Should scientists desert major speech conferences, no ICAS, no Interspeech anymore, for still preserved islands with finals in E, like psychology, sociology, philosophy, or prosody? I claim here that we need a research agenda for mutual enrichment of speech science and technology, building bridges between artificial and natural intelligence for the sake of the comprehension of a complex world. So thanks to the artificial intelligence revolution, speech technology has reached an amazing level of performance. Last year, we organized in Grenoble the 12th Speech Synthesis Workshop and the 18th Blizzard Challenge. For the first time, TTS were competing on French. Respectively, 18 versus 14 teams sent their synthesis for the hub and spoke task. The spoke task was rather challenging because of limited speech provided by a female local comedian. But amazingly, the best system F, that circle with the red color on the screen, fools similarity ratings of relatives of that comedian, parents, husband, children, friends. In short, TTS models nowadays generate signals which are almost equivalent to original recordings. So let's postulate that generative models can be used as a reliable proxy between scientists and data. They do a good job extracting regularities from data, so let's probe them. Instead, these models provide a comprehensive description of multimodal data provided in extenso, could be speech, text, videos, mocap data, labels, and so on. So human expertise may be enriched by extracting knowledge from this data summarization. In the following, I will introduce methodologies for visualizing and extracting meaningful data representations built by these deep models. And we hope that in return, such data representation, also called latent spaces, can be biased by a priori scientific knowledge or comprehensive models built from human expertise. So our research agenda aims at providing a better interface between speech science and technology for the sake of increasing human comprehension on observed phenomena. Let's move to the scientific part. I will illustrate my claim with two recent works. The first one is the result of a Martin Lenglet PhD student supervised by Olivier Perrotin and myself, where Martin analyzed the latent phonetic representation built by end-to-end TTS systems. The second one concerned the construction of multimodal large language model for generating audiovisual expressive synthesis. This multimodal large language model, MLLM in short, embeds objective descriptions of audiovisual signals together with verbal descriptions provided by human viewers in a common human readable semantic representation. Let's start with a probing of latent representation of TTS. In machine learning, a latent space is an abstract multidimensional space that encodes a meaningful internal representation of externally observed events. The key idea is that samples which are similar in the external world are positioned close to each other in the latent space. The building of latent spaces consists, in fact, in substituting a semantic similarity with an objective distance between vectors and tensors encoding the original samples. Such embeddings, and that's the term, embeddings of samples onto these latent spaces are usually learned by an encoder-decoder architecture that projects some observed dimensions of the samples onto a compact latent space, the yellow box in the middle here, that is further decoded, in fact, to predict the same. This is called self-supervision. Variational autoencoders, called VAEs, are often used to better structure the latent space. The encoder predicts not only a value, but a distribution, mean and standard deviation, that is further sampled before being decoded. Of course, a priori semantic knowledge on the underlying events can be introduced to constrain. So the idea is the keyword is to bias, in fact, the latent space manifold by external features, using either classification losses or partial regression losses. As an example, I give two examples here. Barlow et al. Proposed to constrain an autoencoder to build a latent space that discriminate between predefined classes to probe clinical metabolic data. Similarly, my colleagues George and al. Proposed recently to constrain an acoustic autoencoder to partially use articulatory data as intermediate representation, since acoustic is just, in fact, the byproduct of an articulation and a phonation. Instead of explicitly biasing the latent representation by external label and signals, downstream tasks, a posteriori classification or regression, can be also used to probe, in fact, the discriminative or predicted power of latent spaces built at different levels. Valdaya, oh, sorry. What's the hell? Okay. Well. So Valdaya et al. Exploit performance of different layers in 4 different self-supervised speech models in predicting filter banks features, spatiotemporal features, phenome identity, and word identity by classification task from frozen self-supervised speech models. They show, for example, that upper middle layers in wave-to-vec and Hubert best encode phoneme and word-level information, while the lower layers are better at predicting acoustic features. Intermediate layers are often the most informative for identifying phonemes and words. In the same spirit, Cho and al. Demonstrate that wave-to-vec and Hubert behave quite differently when asked to predict articulatory features. This linear probing could be used not only to evaluate discrimination performance, but also to provide relevant control spaces in the latent space. Yang et al., for example, introduce what is called causal inference, consisting in identifying the optimal direction in a given latent space that best discriminate between two semantic properties. So using a style-based architecture for generating images of outdoor, bridges, churches, towers, and indoor scenes, living rooms, kitchen, where the objects, their layout and properties have been a priori labeled, they notably show that direction in the latent space can be identified a posteriori to control most of its properties. Here, the increase or decrease of lighting of the indoor scene is displayed. You can see by switching this vector to 2.57 to 0.3, you switch between a dark sleeping room to a daylight sleeping room. And it's quite interesting to see that you have covariations. For example, you have the increase of lighting means a switching of light balls in the right figure. So in the following, we will use this technique to control the generation of pauses and liaisons in our end-to-end TTS. So in the following, we will apply linear probing to two emblematic end-to-end text-to-speech systems, Tacotron 2, and FastSpeech 2. Note that the HEF system that won the Blizzard Challenge 2023 uses FastSpeech 2. All systems, including recent diffusion models, have an encoder-decoder architecture where input symbols characters or phonemes are contextualized by the encoder in blue in both architectures, then warped to audio frames via an auto-attention mechanism, that's Tacotron, or an explicit duration predictor, that's the FastSpeech 2, and the decoder in green further converts these phone embeddings into spectrogram. These are further transformed to signals via neural vocoders. We used here IFIGAN. We trained both systems on the same training and test data. We used a new segmentation of the French MEI Labs datasets, uttered by a French female speaker, Nadine Edert-Boulet, that preserves original book structure. We have shown that the segmentation impacts quite a few of the synthesis quality. We have about 30 hours of good quality audiobooks recorded by the speaker. For each utterance, this corpus includes both the orthographic and phonetic transcript. Note that the phonetic transcript keeps word boundaries and punctuation marks. So we just play. We also performed a one-to-one letter-to-sound mapping for this corpus. This letter-to-sound mapping is based on empirical rules derived from the analysis of attention maps of the Tacotron 2 model. We highlight here in red color the characters that do not correspond to any phonetic production in the sequence. They are called mute characters that are marked as underscore, in fact, in the phone mapping. So this letter-to-sound mapping was used to explore how phonetic representation arise from orthographic sequences in the French opaque writing, which is not the case of Italian or Spanish. Sorry. In practice, we use this letter-to-sound mapping to train categorical predictors from intermediate latent spaces. So taking fast speech as an example, the idea is to predict in which layers the phonetic sequence, including mute signs, can be predicted from input characters. For each layer, we evaluate the F1 score, which indicates the accuracy of this prediction, between 0 for poor prediction to 1 for perfect prediction. Results are quite similar. So the results are reported here by layer, from the phone embeddings to the last layer for fast speech here, for the left on the decoder on the right. As you can see, phonetic representation do appear quickly in the model. Right from the start, accuracy on stop consonants, for example, which are displayed in yellow, is very high, whereas vowels in red need at least one contextualizing step to reach similar score. This difference is at the very beginning is explained by the variability of possible phonetic outputs for vowels compared to consonants. In any case, after the first transformer layer, most embeddings seems to encode the phonetic target. Results are quite similar for Tacotron 2. The first convolutional layer seemed to be enough to contextualize most letters. This visualization also unveils that the classification of liaison in green and silences in purple, despite being intuitively a similar task to phonetic prediction, requires much more steps to reach similar F1 score in fast speech 2 and doesn't reach similar accuracy in Tacotron 2. It somehow explains the difference in performance. The encoding of most phonological behaviors are best performed at the end, at the output of the encoder. This made us consider the introduction of an explicit phonetic predictor at this layer of the model. So this subtask uses the one-to-one letter-to-sound mapping as targets and is trained through cross-entropy loss alongside the rest of the model. So while this additional subtask may seem unnecessary because of good scores already performed by the model, these additional targets provide a new training mechanism for the TTS encoder, which is now trainable on phonetic alignments alone, even in absence of audio recordings. For example, in audio books from the beginning of the 20th century, technique, for example, was not very well used. It was not introduced, and in French, it's pronounced most of the time technique. In absence of audio recordings, so we notably use this option to train the encoder on thousands of dictionary inputs and in-context transcripts. This subtask reaches more than 98% accuracy on a test set comprising 2,000 utterances. Most remaining errors are indeed confusion between mute letters and silences. Commas, dots, and so on, pronounced or not, silences. And also at potential liaison location, te, de, ne, ze. Nevertheless, this phonetic predictor competes with state-of-the-art letter-to-sound frontheads like eSpeak. This emphasizes the benefits of understanding the underlying representation learned by neural architecture and designing meaningful subtasks. Let's explore now latent representation of continuous prosodic features. So prosody. We took the R-square value as an indicator of a goodness of fit and report here, once again, the evaluation by successive neural layers. We selected 4 well-known prosodic features: log duration in green, F0, light blue, spectral tilt, ST in yellow, energy in red. And we also explored one phonotactic variables, relative position of the input sequence, RP, in dark blue. We'll comment on this. As you can see, the encoding of prosodic features require more layers than the phone prediction previously analyzed. In FastSpeech 2, on the right side of the slide, at the output of the encoder, duration, pitch, and energy have been encoded, and there is little to no changes later in the decoder. Tacotron 2, on the other hand, shows a similar behavior, but it needs the recurrent layers in the decoder to fully encode pitch and energy. Note that the spectral tilt is encoded later in the decoder in both cases. Takes the decoder. So the relative position always shows an interesting pattern. Despite being explicitly provided twice in FastSpeech 2 with so-called positional encoding, this information vanishes through the successive layers of the encoder and the decoder. So this visualization illustrates why the positional encoding is also needed at the input of the decoder, so the second time, despite being already given as input in the encoder. Conversely, VRP is implicitly encoded by Tacotron 2, which seems to need this information, close to 0.9. So, but why we have this difference in FastSpeech 2 between duration, pitch, and energy on one hand, and spectral tilt on the other? As a matter of fact, FastSpeech 2 implements 3 explicit predictors for duration, pitch, and energy, which are trained with the rest of the model to compute these 3 values. In absence of speech and energy predictors in the left panel, these 2 features follow the same behavior as in Tacotron 2. So we first show that we were able to exhibit to understand the presence of this an impact of these prosodic features, even in absence of explicit predictors. This visualization tool provides new objective evaluation to compare the behavior of the model, depending on their architecture. Future work, we should extend this analysis to more variation of the architecture and models in order to explore the consistency between the computation of prosodic features and perceptual judgments. Finally, this identification of features that are linearly encoded into neural layers offer potential placement for this causal control I introduced in the introduction. So this identification of features linearly encoded into neural layers offer potential causal control placements. But this is not sufficient. This representation should be effectively used to compute the output spectrogram. Could be computed but not used. So we first selected layers that exhibit maximum correlation values as candidates for causal regressor, and then examined the effect on the output features by varying the regressor within the ±3 standard deviation of their empirical distribution. For some layers, the effect is null. See the output of the conv1 layer for the control of F0 in Tacotron 2. So for F0, the correlation is not high, but the output is 0. So the information somehow is there, but it's not used directly by the decoder. In large networks, sometimes the information often is duplicated. On the contrary, the causal regression of F0 at the output of a BLSTM layer can be effectively used to control the F0 output with clear saturation effects, modeled as sigmoids in the final nonlinear regressor. It offers a very precise control, roughly over the range plus -2 standard deviation of the F0 output. On the right figure, we can see that the BLSTM layer, the output of Tacotron 2 text encoder provides optimal control for all prosodic features, not only F0, but also energy, spectral tilt, and so on. So I won't elaborate on the evaluation. We performed the whole evaluation. In the following, we choose the output of the encoder to implement all controls. Here is an example of control of F0 register. So let's listen to the unbiased red curve.
Oh, sorry, Gérard, it's not.
It's not playing? It's not playing?
No.
You don't listen to it? Sorry. Well, you listened before, but now you can't listen.
No, I listened the test at the beginning, but now since you have the slides from slide 2 on, we don't hear anything.
Okay, let's believe me. At least in French, it's in French. So this control provides interesting behaviors compared to just shifting VF0. Notably, this example shows two main effects. Saturation effects appear both for high and low values. This saturation matches the extreme values of the F0 distribution seen in the training corpus. The fact that this control respects these limits is encouraging in terms of naturalness. The second is that the ending tone is also modified. The global lowering of F0 produces a flat tone instead of an unbiased rising tone. This change of tone is likely due to the model having learned that utterances produced by the speaker with a low mean F0 tend to end with a falling tone. Again, this control benefits from statistical co-occurrences in contrast with explicit disentangled prosodic control. So this causal regressor can also unveil the way end-to-end systems build each output feature. This is particularly interesting for systems using feed-forward transformers, since this layer adds modulations to the previous one. It's really a cumulative superpositional model. I will show you here how the F0 contour of a sample utterance is predicted by the layers of the text encoder, the prosodic predictors, and the final acoustic decoder of fast switch 2. So the target F0 is figured here in red, and the F0 predicted by the layer-specific causal regression is in blue. It will evolve in the network. The black arrow indicates the layer in the fast speech 2 architecture, where we in fact compute the F0. Here, the first embedding layer seems to preset microprosody. For example, A and O phones are F0 lower than E and U, but higher than the M consonants. So it's logical. The embedding layer knows about the identity of the phones, and it can preset, in fact, microprosody. But of course, this will be modified afterwards. So just unveil the progression of this F0 contour in the different layers. Second layer, where you add the positional encoding. Tac, tac. So encoder, energy predictor. So when moving into the decoder, the prediction is not made phone by phone, but frame by frame. So that's why you have more finer modulation. Tac, 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 tac. And the acoustic decoder then provides a quasi-perfect F0 contour, ready to in-paint the harmonic amplitudes in the bands of the output spectrogram. We found the same nonlinearities for duration control as observed for VF0. In a study published at Interspeech 2022, we have showed that the control of form duration also exhibits saturations, especially with final vowels and silences, as in the ground truth, which is figured in black. Which is not the case when stretching the speech or just multiplying all duration of the duration predictor of fast speech 2. We also highlighted that both our methods and the explicit control did not modify the proportion of silences at word boundaries. So we are a bit disappointed. So the contrary, ground truth, figured in black, produces more and less or less silences depending on the average duration of a form. Well known, when you increase duration, when you stretchen the speech, you produce more silences. It's more economical. So although this result shows that the encoding of duration is not collinear with the encoding of silences, can we adapt the proposed method to correlate speech rate with proportion of silences? From the control perspective, this linear discriminant analysis we previously used to perform the prediction of silences present the same benefits than the multilinear regression. Assuming that each one of these two classes follows a Gaussian distribution in the embedding space, VLDLA, linear discriminant analysis, computes the linear combination of dimensions that best separates these two classes. As a result, the LDA, the linear discriminant analysis, also exhibits one preferred dimension in the embedding space, which is susceptible to encode the switch between production or not of silences. By moving, in fact, this embedding along this direction, which is equivalent to add a linear bias to all embeddings of a sequence, it is possible to control the model tendency to produce more or less silences. So I will try just to play, but if it's not audible.
No.
No. Okay. So here we produce no silences. Here it's no bias, so you have at least 3 silences, and here you have a silence at almost every word. So the challenge is now to generate intermediate amounts of silences by scaling the magnitude of the bias according to the duration bias, following the ground truth behavior of our speaker. So first we combine the control of duration with the control of the production of silences at word boundaries. So see the red boxes, in fact, the 3 red boxes at the bottom that are not present if a naive stretching of the iterant is applied, which is performed at the middle spectrogram. Note that, so no listen. Note that we did not explicitly choose where the model should add these silences, but the linear bias is expected, in fact, to trigger the appropriate silences and their duration from the textual content. Of course, additional information about syntactic structure, such as provided by BERT embeddings, would also help. So conclusion, the combined control show interesting properties in terms of natural control of speaking rate. Notably, we showed that the encoding of duration and the silence triggers were disentangled, and that the combination of these two biases were needed, in fact, to achieve a satisfying control. So thanks to these examples, we also emphasize the versatility of the proposed control. We also evaluated this control on 5 segmental features that I have not discussed here. Note that this control does not require any additional training for the model, nor additional datasets. The causal control emerged from analysis of TTS embedding, as is somehow provided for free. However, note that the control provided by this method is not as supervised, as predictable as an explicit control. As a result, perceptual evaluation have not yet shown or clear preferences for either the method or classical explicit control. We think that more constraints should be added, such as avoiding the production of silences at inappropriate word boundaries, for example. So the analytic tools, which are proposed here, could be applied to other models to provide similar control, even in absence of explicit predictors. Let's summarize the key issue of the first contribution. So analyze models instead of the data, since they are likely to have captured regularities between text, speaker, and style, as well as covariation between features that are often beyond our expertise. Think about latent embeddings as a genetic chain that embeds genes to be expressed in the signals as local or global features, shaping phones and phonetic spaces like formants, F0 duration, and so on, as well as phonological units such as phone, syllables, breath groups, and so on. Processing layers, so-called biased, could be from the speaker, style, or whatever, and predictors gradually shape these genes to take broader and broader context into account. So just mention that these feed-forward transformer are basically superpositional models that refine step by step, produce prediction. The same process applies for diffusion models. So this could feed debates on the nature of prosodic representation. So let's move rapidly to our second contribution, how multimodal large language models, MLMs in short, can help us exploring functions of prosody and how forms and functions are associated. Nowadays, a major challenge of TTS is to bias text-to-speech models with paralinguistic information, such as speaker identity, mood, or expressivity. This is usually performed by adding and concatenating identity, mood, expressivity embeddings to each contextualized embedding at the output of the text encoder. Here is given the audiovisual expressive TTS model we have developed with Martin and Olivier in the second part of his thesis. The standard FastSpeech2 has been augmented by, enlightened in one, a constrained global style token, so-called GST, introduced by the Google group, a module that estimates weights of style embeddings thanks to a combination of a reference encoder, summarizing the acoustic variants not yet explained by the text, and predefined style tokens, here 12 instructed emotions, I will introduce later. This bias is added to all phone embedding of the utterance. In second, in black, the phonetic predictor we have already discussed. Third, speaker embeddings are adding before the phonetic predictor, and of course added to all phone embeddings of utterance. In fourth, a visual decoder with specific predictors to predict facial movements. A local style token LST module, which adds, in fact, modulation specific to units of utterance as a function of a GST output and the text encoder. We used word units in the following. Note that the GST and LST bias can be weighted to reflect gradients to the intended styles. I will not listen to speaker embeddings because we don't have any sound, sorry. So our expressive data come from 30 hours of emotional corpus recorded by a French female professional comedian in Grenoble. She shared extract of Swiss utterances with 12 different attitudes. So angry, committed, enthusiastic, playful, surprised, obvious, skeptical, thoughtful, comforting, pleading, and narrative. while a phase being tracked in real time by the dynamic XYZ performer. So here we just see the video. So you have normally the original speaker, and you have the animation in real time. Okay. So this avatar is further driven by a dialogue system and our expressive audiovisual TTS to serve as a conversational agent for exercising a patient involved in cognitive remediation. So here are syntheses obtained by setting GST weights to 1 for each individual instructed attitude, while setting others to 0. I think it's I would just stop very quickly just to see if we can restore just for you to listen at least to. So here, what you listen here is sentences, so to text, where I set the GST weight 1 for the desired emotion, of course 0 to the others, just to enjoy playful, for example.
Bonjour et bienvenue à toutes et à tous pour cette présentation de la version expressive de la voix thérapie.
Okay. So, of course, instructed emotion can be mixed, but the problem is how to set weights, in fact, to reach a targeted emotional nuance, and how to cope with variability of training performances, because the woman has been instructed to perform a certain emotion, but perhaps she already performed a nuance. So the scientific challenge is to explain variability around prototypes, not using adult weights, what is per se 80% of enthusiasm and 20% of skepticism, but in fact we will be using verbal input. So to use words like stupefaction or daze.
Bonjour et bienvenue à toutes et à tous pour cette présentation.
So what we introduce is a style encoder, which will be trained jointly by signal-based reference encoder. So as I said, part of a signal which is not yet encoded by or explained by the text, but also verbal-based encoder driven by SBERT encoded emotional tags. So this will be it has been quite strongly inspired by 2 papers presented at Interspeech 2001 and 21 and 22 by Korean groups. So so here you have a reference encoder which receive in fact the same reference speech as the target. We want to the TTS system, in fact, to encode the style which has been given as in the signal in the target signal. So in both systems, you have a reference encoder, and you have also this. You have a alternation between this the training from the reference encoder, but also from style tags, which are go through a BERT system with adaptation layers. And Shin and all the last, they use 5,000 unique verbalizations to train, in fact, the reference encoder. Note that these 2 systems were addressing the synthesis of the big 6 emotions, so happy, sorry, disgust, and so on. We adopt a quite similar approach, but we collect massive data. We'll see combining free and semi-directed selection of tags, of verbal tags, adjectives, qualifying in fact the performance. We explain in fact the variability around extracting emotions, associating in fact, so we keep this GST how to say, mutual representation. So associating GST weights with lexical nuances. Of course, it's in French, it's not in Korean. And it's audiovisual, so the targets and the style encoder receive audiovisual input, action unit for the facial display. And of course, we go beyond basic emotions, so not only big six, but 12 so-called attitudes I have already mentioned. So the data we have collected, we have asking people to rate, in fact, 12,000 audiovisual clips of the performance of our comedian, which has been instructed to perform 12 instructed attitudes. In fact, to help the people, in fact, to tag the clips, we first produce an emotional space by, in fact, selecting a dozen of synonyms for each attitude. We end up with a total of 132 synonyms. And we perform a LDA of the embeddings of these synonyms by the large Flaubert model for French. So we, in fact, we downsample, we compact the 1024 dimension of the original embeddings to 11 discriminant axes using linear discriminant analysis. And here you have displayed, in fact, the first discriminant plane, where you have, in fact, some kind of continuous semantic representation, which is somehow organized around the 12 basic or reference attitudes. So how the people provide tags? We selected, we had an interface via the web, where the subjects are displayed with they can play several times the clip, and they have to associate, to clarify the performance with adjectives. And they can enter adjectives by two ways, either by incremental suggestions via navigation in the emotional space. So at the first time, we have two seed adjectives plus another button. If they select the other 6 most distant adjectives from these already suggested adjectives are proposed. Otherwise, the adjective is selected, and then 6 closest adjectives from the selection are further proposed. The idea is to at least select at least 2 adjectives qualifying, in fact, the performance. They can also provide direct selection by searching or in the list of 132, or provide free input, so they can enter an adjective. So that's you can surf on this side to get the current results. Up to now, we have almost results from 800 annotators. Almost 72% of utterances have been tagged by at least 10 annotators. In total, we have collected 120,000 tags. They used, on average per tag, 13 suggested tags by clicking 4 times on over, versus 0.2 free tags. So most of the time, they prefer to have this semi-supervised or system-driven selection than a free task, because sometimes you have just the adjective on your tongue, but you can't find it. So the navigation helps us, in fact, help the people, in fact, to get the proper adjective. Just to mention that we collected, however, 323 adjectives with a count superior to 2 as free tags. So altogether, they are put in the BERT system. We collect, in fact, their embeddings, the word embeddings. And oh, yes, I have an extra slide. So we have here the collected adjective per original attitude. So you have the 12 schemes here. So it's a good characterization. The first, the most selected adjective is mostly corresponding to the first one. But for some attitudes, which are comforting, skeptical, and pleading, you have a more punchy, in fact, distribution. It's less picky than the others. Altogether, in fact, we explain by word tags, by these verbal tags, almost 70% of the acoustic embeddings computed by the reference encoder altogether. Except for the narrative, because narration is perhaps less well-defined. So the idea is that the reference encoder, so on the left part, and the verbal tags are combined, in fact, to predict the weights of the GST. So the GST, instead of having the 12 original dictionary, in fact, of embeddings, we added, in fact, so we keep 11 tokens for the expressive instruction, and we augment, since narration is a bit more fuzzy, we add 4 free tokens for narration. So altogether, 15 tokens instead of 12. Okay. So what is coming out from this? So you see that, in fact, it's as for the adjectives, the distribution of weights is of course most of the time correlated with the instructed attitudes. So angriness, it's close to 1 for the first token. Sorry is maximum for the second token, third token, fourth, and so on. You can see that neutral, or the narrative part, is a bit fuzzy. Is more somehow the style token, which is the most recruited for narration or for neutral, is committed. It's the third one in orange, which is not surprising, because she knows about the application, so she wanted to encourage, in fact, the elderly person to perform the exercises. So as I said, most of the time it's mirroring, in fact, the Gaussian distribution around the instructed emotion, but we have a spreading of activation, especially for narrative. The four extra tokens are mostly unused, so it seems that the basis of 11 is sufficient enough, in fact, to somehow navigate into this prosodic space, expressive space. So I will just perform 4 demos, illustrating the fact that we can, of course, perform poor style tagging. For example, if you enter be angry, the style tag angry is recruited with activation of 0.999. So is giving this.
Je vous souhaite la bienvenue à cette présentation du projet Emotag.
Very convinced.
Je vous souhaite la bienvenue à cette présentation du projet Emotag.
When we enter surprised, surprise is activated at 1.0, so maximum, of course, and it's normally synthesizing surprised.
Je vous souhaite la bienvenue à cette présentation du projet Emotag.
Okay.
Je vous souhaite la bienvenue à...
So what is more interesting is to enter a nuance. So a tag, an adjective, which is not part of the initial set of synonyms. So like being kind. And when you enter kind, in fact, it's recruiting, in fact, 2 verbal tags with 0.6 for enthusiasm and 0.38 for comforting. And this is giving this...
Je vous souhaite la bienvenue à cette présentation du projet Emotag. Je vous souhaite la bienvenue à cette...
And last one, when we enter lawful, we can even have a recruitment of 3 different style tags. Skeptical, so lawful, skeptical at 0.6, thoughtful at 0.2, and miscellaneous at 0.13. This kind of stuff.
Je vous souhaite la bienvenue à cette présentation du projet Emotag.
Yeah, not so convinced. So the second contribution is that we produce an audiovisual TTS that is alternatively driven by a reference signal, where you can say, you can put a signal and say this, the text, with the style in this other signal, in this reference signal. Another way is to use the GST, so to weight the reference tokens, but you use a restricted set of emotion labels, or you can provide a full verbal description. Now it's limited to a set of adjectives separated by commas, but it could be in a very next future a whole sentence. We have proposed a methodology for studying prosodic functions. We can apply the first solution to explore these joint embeddings via the global and local styles token that provides, in fact, the insights on the coordination between syntax and attitudes. For example, you can think about certain words to be that carries sarcasm or whatever. So you can study, in fact, the coordination between the global instruction, attitudinal instruction, and its local anchors. And of course, it's offers a way to explore phonological variation, in particular idiosyncrasies, because all speakers have not the same way, in fact, to implement, to produce the same attitudes or emotions. And of course, the perspective is to perhaps to have extra input and output modalities, why not neural signals, for example, or new emotion, languages, or situation. If other partners in the audience are interesting to study another language or another set of emotional palette, feel free to contact me.
Thank you, Gérard. What do you think to go to the question?
Yeah, so it's just to share that we propose, in fact, 2 solutions. I want to acknowledge my colleagues, and many thanks for your attention.
Thank you so much. Thank you so much. Now we have time for questions.
The target window cannot be okay. So.
I have a short question, probably.
Yeah.
When we were talking about the prediction of prosody, you told us that you use syntactic information for predicting the position of silences, I think. And do you also use semantic information or only syntactic one?
No. That's what I mentioned. In fact, we didn't use. It was just the text encoder. So of course, to synthesize text to speech, we suspect that the system is somehow. There are other studies that have shown that end-to-end models encode sometimes of some kinds, in fact, of syntactic information. But we could have introduced, and there are a lot of people in the challenge, for example, that have augmented text with BERT tags, so information about words. Here, the input was just text, just the letters. So in the intermediate stages, we suspect that they are some kind of syntactic information because the pauses are not generated randomly. So I suspect that the text encoder is spotting some keywords, some
The length of the word.
You can imagine to help such system by concatenating characters with BERT embeddings. But of course, it's huge models because embeddings of characters are already 700. If you add 1,000 more dimensions, you end up with you need quite a few more data to train such systems.
Okay, of course.
And of course, BERT computes internally some semantic information.
It was also very interesting in the last 4 demos, you combining adjectives for proposing more nuanced display of emotions and attitudes. Very, very interesting. And do you check with the one chain was more helpful in displaying the emotion, the audio, or the visual information? Do you examine the relative contributions of vision and in the expression of this emotion as well?
But we are planning are planning to do so. It's of course first we verified that how to say somehow 70% of what we capture as audiovisual variability is really explained by verbal tags. So we have some kind of information between the two. But the key issue now is really to verify that this joint representation is effectively used, in fact, in the output, and how much is shared between acoustics and visual.
Yes, at the beginning, I thought that the visual was not so important for the first demo, but after probably the second and third, we saw some more changes in the face. And
for example, thinking you have an attitude like this, with the eyes going up and so on. So dupting, for example, you have a bit of roll of the head. So we know that the head component has a strong impact on the perception of there is a visual prosody.
Okay, thank you. And another thing, several times it was clear for us that you are it's very important for you to probe, to have particular information on what each module is doing. Here is micro-prosody, here is try to do something. In your work, you're trying to infer what these black boxes are doing more systematically. Question.
I think I just attended a talk just before, which was invited speaker by this Grenoble Artificial Institute from Bernd Schiller. Where's the guy? Bernd Schiller. And this guy is working on the same kind of explainable eye. There is a tendency, especially in vision, to try to extract, to understand how this vision multimodal large language models are performing decision. about is there a giraffe in the a human, a bicycle, and so on in the image. So to provide, in fact, for the user some kind of where is the information in the image. So at the source. But of course, you can apply this to every. They have been questioned to him for this, so to understand at which stage, in fact, the decision is made, and to understand also, for example, the relations. For example, if you want if the image is a man riding a horse, you have to take the decision about the horse, about the man, and to have also a detection of how to say relations, positional relations between the two. Are you under the horse or over the horse, the side, and so on? So all this kind of semantic description and so on, it's interesting, in fact, to probe the system and to understand how it's computing this. So yes, and as I said, for me, as a technological point of view, is a way also to say this is the place now where I can inject intelligence. So as a prosodic expert, I know, for example, that I don't know, tones or I don't know, accents and so on should be injected as information. Because most of the time in TTS, they put all the information at the beginning, hoping that it will be a mirror in the signal, which is not very efficient as a way of thinking.
Okay, thank you. I think we have no more questions, Gérard. Thank you. Thank you so much for being here, and I hope if people will write to us to ask things on your presentation, because they will watch your presentation the next weeks, then we will transmit this question to you. Okay. Thank you so much.
Thank you.
Bye.
Bye, Gustavo.
Bye. Thank you, Gustavo, for your work.
Bye. Thank you.
You're welcome.
And thank you, our technician Leonardo, for his work as well. Thank you so much.
These three people.
Thank you.
Bye. Thank you.